Hello folks, welcome back. So let's go ahead and review the four caveats that we set up to help us understand this section. The first caveat basically said that you can only use the formula V is equal to integral of K dq over R to evaluate the potential if you're dealing with a finite extent of charge distribution. The second formula said that if you're dealing with an infinite charge, for example, an infinite line charge or an infinite plane of charge, then you must indeed use VB minus VA is equal to minus of integral from A to B of E vector dot ds vector. Okay, so that was our second caveat. Our third caveat said that if you're ever in a situation where your potential has a sudden drop, so if this is your plot of the potential as a function of position, and you have a sudden drop at a given location or a sudden change at a given location, then that is an unacceptable idea because it results in energetically unfavorable situations. And the fourth caveat that we had said, watch out for the constant of integration. So armed with those four caveats, we were able to go ahead and solve several problems associated with electrostatic potential. Well, and the name of the game with respect to solving problems with electrostatic potential is practice, practice, and practice. So we're going to provide you with a lot of other practice problems in this subunit. What I would urge you all to do is basically, if you're going ahead and previewing this material or seeing it for the first time, go ahead and look at the solutions so that you can help yourself. But if you're reviewing this material, namely looking at it a second or third time over, then go ahead and pause the video at the point where I describe the problem and try to see whether you can work the problem out yourself and see how well you fared compared to the solution that I give. And that might actually help you a little more than just passively watching the videos for a second review or a third review or whatever. So with those ideas, let's go ahead and do this problem, which basically tells us that we have an infinite sheet of charge located along the x-axis at x is equal to 0. So think of the x-axis, and the sheet of charge is perpendicular to the x-axis. We're therefore told to first use Gauss's law to find the electric field both for x greater than 0 and for x less than 0. And that's easy to do because we realize that if this sheet is positively charged, we can go ahead and have our closed Gaussian surface to be a pillbox which projects out from one side into the other side of this sheet. And therefore, we can say that the flux through this surface is just given by E times A, where A is the area of the flat part of the cylinder. The flux through this surface is also given by E times A. And therefore, we have a situation where the total flux is just given by 2 times E times A. And that should be equal to the charge inside. So we evaluate the charge inside as being the charge inside the cylinder. That is given by the surface charge density times the cross-sectional area of the cylinder or the cylindrical pillbox itself divided by epsilon naught. And by canceling off the areas, we get E is equal to sigma over 2 epsilon naught. Okay, so if I can erase off the pillbox, I can actually write the electric fields on either side in nice vectorial notation. And so let's go ahead and do exactly that. So we have the electric field out here on the right side being given by E vector is equal to sigma over 2 epsilon naught times I hat, and the electric field for x less than 0 being given by E vector is equal to minus sigma over 2 epsilon naught times I hat. Okay, so this gives us the electric field in vectorial notation for x greater than 0 and x less than 0. And now let's say that we want to solve part 2. Notice that this is an infinite sheet of charge, and so we've been very conveniently told that we can set v is equal to 0 at x is equal to 0. Namely, at the location of the sheet itself, we can set the potential to be 0. This tells us that if we want the potential at any location x greater than 0, then we can go ahead and say that Vx minus v at the location x is equal to 0 is just equal to minus of an integral from 0 to x of E vector dot dl vector. Now notice that E vector is just this guy, which is oriented along the positive x-axis. And if we're going to make a displacement dx, then this dl vector is also equal to the displacement dx in the positive x direction times I hat. Therefore, d E vector dot dl vector is just sigma over 2 epsilon naught times dx itself. And this integral is easy to do because sigma is a constant, 2 is a constant, epsilon naught is a constant, and so the integral turns out to be just minus sigma over 2 epsilon naught times x itself. Now notice that we've been told that v at x is equal to 0 can be set to 0. So we set this guy to be 0, and we obtain the potential as a function of x to be equal to minus sigma over 2 epsilon naught times x for x greater than 0. Notice that if we take minus dv by dx, we basically retrieve the electric field for x greater than 0, which is exactly as expected, and that is a very good thing. Now, the situation becomes a little more intricate if we consider x less than 0. So let's consider a situation where x is less than 0. Now we would actually like to integrate from x less than 0 to all the way up to x is equal to 0. So we have essentially as our integration v0 minus vx as being equal to minus integral from x to 0. Notice that in this case, we're considering x less than 0. So integrating from x to 0 is actually an integration along the positive direction of the x-axis. And then we essentially have our electric field for x less than 0 being given by minus sigma over 2 epsilon naught times I hat. And this guy is dotted to the displacement, which is in the positive x direction, so we write it as dx times I hat. Okay? So we get, as our integration, we get minus x to 0 of notice that I have a minus sign here and a minus sign here, which basically means that I can go ahead and eliminate the negative sign. So I'll do exactly that. You should always make your solution as simple as possible, as quickly as possible. And so you obtain an integration from x to 0 of sigma over 2 epsilon naught times dx. Okay? And that integrates to minus sigma over 2 epsilon naught times x itself. Now notice that V0 is given to us as being 0. So we set it to be 0, and notice that we still have a minus sign lurking out here, which actually allows us to say that Vx by itself is equal to sigma over 2 epsilon naught times x. This is the solution for x greater, or I'm sorry, x less than 0. Okay? So if we were to plot it out, we would actually have a situation where the plot of v as a function of x would be negatively sloping for x greater than 0. Notice this one. And Vx as a function of x, or I could write it as Vx as a function of x, would have a positive slope for x less than 0. And that is consistent with the fact that the electric field is positively oriented for x greater than 0 and negatively oriented for x less than 0. So we see how to solve problems with infinite charges in its simplest setting. Now, let's go ahead and do another problem. This problem pertains to a shell of charge on which we have placed an amount of charge q. So this shell has a radius a, and on the surface of this shell, when we say shell, think about a basketball. It has nothing on the inside, it has only air on the inside, and the charge can only locate itself on the surface of the basketball. In that case, what we have learned from our study of Gauss's law is that for r greater than a, the electric field for this situation behaves exactly as you'd expect for an electric field with a charge that is entirely concentrated at the center of the sphere itself, or the spherical shell itself. So E is just given by K times big Q divided by the radius R, where R is the radius going from here to here. Okay? And this times R hat. Now, we go ahead and ask ourselves, what is the change in potential as we go a certain distance dr in the outward direction? And that is just given by minus kq divided by r squared times dr, which basically reminds us that this is the same formula that we used for finding the potential associated with a point charge. And therefore, we expect that for r greater than a, we have our potential being just given by k q divided by r for r greater than a. Okay? So that's the idea. This actually tells us that the potential exactly at the surface of the sphere, as measured from the outside direction, is just given by V is equal to KQ divided by little a. Okay, so we see now that if we wanted to plot the potential as a function of radius, which is done out here, V as a function of r, then for points r greater than or equal to a, we have V going as KQ over r, exactly as we expect for a point charge of similar charge, which is located at the center of the sphere itself. Now let's go ahead and ask, what is the potential in the interior of the spherical shell? Notice that the spherical shell is devoid of any charge on its interior. And therefore, from Gauss's law, we can deduce that the electric field in the interior of the entire spherical shell is exactly 0. Therefore, if we take any 2 points, maybe a point here and a point here, and we connect them by a straight line, we realize that the potential difference between these 2 points must be exactly 0, because the potential difference between two points, VA or VB minus VA, is just equal to minus integral from a to b of E vector dot dl vector. So if this is the point A and this is the point B, we realize that because the electric field inside the spherical shell is exactly zero, then the potentials between any one point and any other point inside the sphere must be exactly equal to zero. What does that imply for the potential? Now, realize an important fact, which is that the potential on the surface of the sphere out here was identified to be kq over a. It means that I can connect this point out here to any other point on the interior of this spherical shell and say that the potential difference between these 2 points must be exactly zero. That means that the potential at this point on the interior of the shell, in anywhere inside the shell, should indeed be the same as kq divided by a. This is why we decide that, now recall that the potential cannot have jumps at any location, and therefore the only way we can avoid a jump and have the same potential everywhere inside the sphere is if the potential is exactly flat and equal to kq over a at all points inside the sphere. So this actually allows us to understand why we have a flat constant potential inside the sphere. But notice that this potential is not zero. It is actually kq over a. And if you set it to zero, then you will actually be generating a finite jump in the potential at this location, which would be unacceptable considering our caveat number 3. So that actually gives you a good idea of how to deal with situations where there is no electric field, how to connect the potential at one point to the potential at another point in such a situation. So I hope this gives you an idea about how we would draw this potential as a function of radius, which is actually the main presentation in this problem. So how we would get the potential as a function of radius for points r greater than a and for points r less than or equal to a. For points less than or equal to a, the potential is a constant, but please remember that it is definitely not zero, okay? If you got a zero answer, then you get 0 points. So that's an important thing to remember. Okay, so with this, let's go ahead and move on to the next problem. So we've seen what happens to the potential outside and inside of a spherical shell of charge. Now let's go ahead and focus on the potential outside a spherical ball of charge which has a uniform volumetric charge density. In other words, this ball of charge is definitely an insulator, and you can think of it as being analogous to a watermelon with a radius a, which has seeds in it that are charged. So you have the same constant charge density at all locations inside this ball of charge. With that, we now realize that the electric field on the outside is still given by kq divided by r squared. Therefore, the potential on the outside should still be equal to kq over r. So for r greater than a, we say that the potential is exactly as we would expect for the potential of an analogous point charge that is located at the center of the ball. Now, for r less than a, we can use our closed Gaussian surface, maybe a closed Gaussian surface that we set up out here like this. And I will not repeat the calculation, but you will actually realize that from chapter 22, we have already found that the electric field is given by this formula. In other words, the electric field increases linearly as a function of r. So our job is to basically go ahead and find the now that we know the electric field as a function of r, our job is to basically go ahead and find the electric potential at all points within the spherical ball, okay? The ball which has a uniform charge, volumetric charge density all over inside of it. So let's go ahead and work that problem. So for r greater than a, we say that v is just equal to kq over r. Therefore, at r is equal to a, coming from the outside, we say that v is actually equal to kq over a. That's good information to have. Okay? Therefore, now let's go ahead and also recall that for r less than a, we have the formula which basically says that E is equal to kq r divided by a cubed. That we get from Gauss's law, and we've studied this application of Gauss's law to a spherical charge density in chapter 22. So we won't repeat that exercise, but I'll just hint to you that you can actually go ahead and derive this result by picking the closed Gaussian surface with a radius of r like so, and evaluating the exact charge inside and obtaining this answer. So with this understanding, we are now interested in finding the electric potential for points r less than or equal to a. Okay? For points r greater than or equal to a, we found already the electric potential, and we realize that for r is equal to a, we have v is equal to kq over a as evaluated from the outside. Now let's go ahead and focus on the inside of the sphere. Now, if I want to go ahead and integrate this electric field as a function of radius inside the sphere, I can actually go ahead and start at the center of the sphere and integrate it outwards to some radius r. So I can go ahead and say that Vr minus V0 is just equal to minus of integral of E times dr, where this E times dr is integrated from 0 to little r. In other words, there's a slight overloaded notation with respect to the use of little r, but don't worry about that, that will work out. So we actually go ahead and say that this is equal to minus integral from 0 to r of kq r divided by a cubed times dr. Now notice that kq over a cubed just slips out of the integral, so we can write this as minus kq divided by a cubed. And inside the integral, we have just 0 to r of r dr. And that is a very easy integral. Integral of r dr is just like the integral of x dx. And the integral is just x squared over 2. So now we get r squared over 2. So we obtain this result as minus kq over 2 a cubed. I'm sorry, let me just go ahead and erase this. So we obtain minus kq over 2 a cubed, and then we have r squared. Okay? Now, notice something very important. I can write this as Vr minus V0, where V0 is in fact the potential at the center of the sphere. Now, why should we take V0 to be not equal to 0? We should take V0 to be not equal to 0 because we want to use V0, which is effectively acting like an integration constant, to match the potential exactly at r is equal to a. So we have a situation where v evaluated at a from the outside is exactly equal to kq over a, just as we did a few minutes ago. So we have kq over a. V evaluated at r is equal to a from the inside is obtained from this formula and is obtained by setting r to be equal to a in this formula. So we obtain this as being equal to v0 minus kq over 2a cubed times r squared, where indeed we have to set r is equal to a. So we obtain this by setting r is equal to a, we obtain v0 minus kq a squared divided by 2a cubed, and so a factor of a squared cancels, and we get divided by 2a. Okay? If we equate the potential from the outside to the potential from the inside, we get our condition for matching the potentials at this boundary. And so we can go ahead and say that v0 minus kq divided by 2a is equal to kq divided by a. Okay, which tells me that the constant v0, which is the potential at the center of the ball, should be equal to 3kq divided by 2a. This is the condition needed to ensure that we do not have any sudden jump in the potential at r is equal to a. So that's very important. Okay? And that gets us through our caveat 3. So we essentially realized that we had to be very cognizant of the constant of integration in order to avoid a jump in the potential. So with this, we can go ahead and stick our expression for VR for r less than a. So we obtain VR. And we go ahead and use this equation that we've derived before, but we specialize it with the v0 that we have obtained in the previous equation. So we get VR is equal to 3kq divided by 2a minus kq r squared divided by 2a cubed. Okay? And I can go ahead and write this in a convenient notation. So I obtain kq divided by 2a, and then I have 3 minus r squared divided by a squared. Okay? So this allows us to actually verify that we can obtain a continuous charge distribution. Notice that because of the minus r squared, this potential on the interior of the ball actually has a parabolic shape which is facing downwards. Okay? And of course outside you have a 1 over r dependence in the potential exactly as expected. So we understand all aspects of this problem. And now let's move on to the next problem. So in the next problem, we're given a line of charge. This line of charge has a linear charge density lambda. And the first part is very simple. It basically says, go ahead and please find electric field using Gauss's law. So as usual, for an infinite line of charge, we basically focus on a section of that charge. And therefore, we can now write the the flux as just being equal to, if we take this closed Gaussian surface that is shown in blue, we can write the flux through that closed Gaussian surface as being given by E times 2 pi R times L, and that should be equal to the charge inside, which is lambda times L divided by epsilon naught. L and L again cancel, and we obtain E as being equal to lambda over 2 pi epsilon naught times R. And if I want to write it in terms of K, I can multiply numerator and denominator by 2, and that allows me to write it as K times lambda times, of course, the factor of 2 divided by R itself. So this gives me the electric field for points outside of the linear charge density itself. Now, in part B, we're told to go ahead and obtain the potential at any point R out here, namely this is R, if we're told what the potential is at some location R is equal to A. So we're going to have to integrate from R is equal to A to some general value of R, and that's exactly what we're going to do using this formula out here. Notice that this formula is very suitable for use with infinite charges because it incorporates naturally the fact that we're being told in this problem that there's a reference potential set to be 0 at R is equal to A. So now we can write VR minus VA as being equal to minus 2k lambda divided by R times dr, and this has to be integrated from A, where the reference potential has been given, to R. And notice that we can write this as minus, and 2k and lambda can be pulled out, and we integrate from A to R of dr over R, and dr over R is just natural log of R, and so we can actually go ahead and write this as minus 2k lambda times natural log of R over A. Okay? With VA set to be 0, which is what the problem specification tells us, we can actually go ahead and set this to be 0, and we can actually obtain our final formula, which says that VR for this particular problem with this constant at R is equal to A is just given by minus 2k lambda times ln of R over A. Okay, so this tells us how to obtain this, and I'll close out this bracket, and this tells us how to obtain the potential at any radial location given the potential at a specific radial point. And we need that because we're dealing with essentially an infinite line of charge. So with this, let's move on to what is perhaps the last problem in this set. Okay, and this problem describes a situation where we have a charge, we initially have an uncharged conducting spherical shell, which is the outer pink shell that is shown to you out here, and it has an inner radius of A and an outer radius of B. We have a point charge Q, and that is placed at the center of this spherical shell. Now, what does the point charge Q do? It basically goes ahead and induces a charge of minus Q on the inner boundary of the shell, and a charge of plus q on the outer boundary of the shell. How can we say that? We can say that because we know that the electric field inside the conducting shell is exactly equal to 0. If the electric field inside the conducting shell is exactly equal to 0, then over this blue closed Gaussian surface that I've drawn, I must have 0 flux. And therefore, if I have 0 flux across the blue closed Gaussian surface, it means that the total charge inside must be equal to 0, which means that the only way this can be achieved is if there is an induced surface charge of minus q on the inner boundary of this conductor. Of course, if an induced charge of minus q goes to the inner boundary of the conductor, an induced charge of plus q goes to the outer boundary of the conductor. And so that is the arrangement that we have. We can also draw this green closed Gaussian surface and come to the conclusion that the total charge inside is just plus q minus q plus q, which is actually just q itself. And therefore, in the exterior region, we still have the electric field being equal to k q over r squared. And therefore, the only potential that we can have in the exterior region is given by V is equal to kq over r. In other words, this potential is the only potential that is consistent with going to 0 at r is equal to infinity. Now let's take these ideas over to this next plot out here and go ahead and draw the potential as a function of radius for all radii. So notice that on the inner boundary of the shell, we have a charge of minus q. On the outer boundary of the shell, we have a charge of plus q. We also have an electric field in the exterior region given by kq over r squared. And correspondingly, we also have a potential which is equal to kq over r. Therefore, at the radius r is equal to b, we should have a potential as evaluated from the exterior, which is given by kq over b. So let's go ahead and draw this situation by saying that for r greater than b, we have a potential that is actually going down as 1 over r. So our potential out here in this region is kq over r, and our potential exactly at r is equal to b is given by kq over b. Now, with this much knowledge fixed up, we can ask, what is the potential difference between any one point and any other point inside this conducting shell? Notice again, just like we had for the spherical shell, we have 0 electric field along any path that connects these 2 points that we have chosen. And therefore, if we have 0 electric field, it stands to reason that there is 0 potential difference between this point out here and this point out here. We therefore realize that all points inside our conducting shell should have the same potential, and that potential should in fact match up with the potential that is exactly at the surface of the conducting shell. So we realize that for all points inside the conducting shell, we have a constant potential out here. Now, this is where the insight begins. We realize that the electric field for this red closed Gaussian surface that lies inside the inner boundary of the conducting shell the electric field out here by applying Gauss's law is still equal to, is still given by K Q divided by R squared. That implies that the potential V should still be equal to KQ divided by R squared, but not quite just that. Why? Because there is always the integrating constant, which I will in this case denote as M. So there's always an integrating constant, and we have to fix up the integrating constant so that we have no possible jumps at any location. I'm sorry, I made a mistake. I should have written this as KQ over R. So the potential in between the charge Q and the inner boundary of the shell is given by KQ over R plus my integrating constant, which is M. So I should arrange for that constant M to be such that there is no jump in the potential. What is the potential at the inner boundary of the shell? The potential at the inner boundary of the shell, as evaluated from immediately outside of it, is still given by K Q over B, because we know that all points inside the shell and at the boundary of the shell are at the same potential. So we want this potential, which is evaluated from this side, to be equal to the potential that is evaluated from this side. Okay? So we want V as a function of R is equal to A as evaluated from the inside, which evaluates to KQ over A plus M, to be equal to the potential KQ over B, which is the potential V at R is equal to A that was evaluated from the outside. Okay, this is an important point. And so we have this equation to be satisfied, and the only way we can satisfy it is by fiddling this constant of integration M. So we get the result that M is equal to KQ over B minus KQ over A, and that allows us to say that the potential VR for points with R less than A is given by KQ over R plus KQ over B minus KQ over A. Okay? So this is the potential for R less than A with the constant of integration M fully fixed up by this previous equation out here. So it tells you that the potential for points R less than or equal to A is in fact given by a 1 over R shape, but with an additional constant added in, and so it will look like this. Notice that there is therefore no jump in the potential here, neither is there a jump in the potential here. So by adjusting the constant of integration correctly, we have arrived at a potential distribution for all radii r, which is devoid of any jumps in the potential. And that's exactly what we needed to do in order to avoid caveat number 3. So with that, we've come to the end of our studies of how to evaluate the potential. And I'll basically thank you for your attention, and I look forward to seeing you all in the next unit. Thank you. Bye-bye.